Pluto, once categorized as a distinct and legitimate planet in our solar system, was considered a special object for many years. However, recent discussions led by famous astrophysicists Neil deGrasse Tyson and Michio Kaku have reignited debate about Pluto's status, prompting further analysis of its role in the cosmos. These scientists have suggested that Pluto could potentially be on a collision course with Neptune, sparking a wave of questions. How could such a massive event unfold? What would the impact mean for both planets and the solar system at large? Are we witnessing a rare and unique cosmic occurrence? Or is there a more intricate and profound explanation behind this theory? Let's delve into what a possible Pluto-Neptune collision might imply. Once considered a smaller, more distant object in the solar system, Pluto still generates substantial interest among scientists. According to key studies from leading experts, Pluto's orbit is dangerously close to Neptune's, causing some astrophysicists, including Tyson and Kaku, to express concern about the possibility of a catastrophic impact between the two. The central question now is whether such an event poses a real threat to Earth. How could this happen in the first place? Pluto's orbit is one of the most unusual in our solar system. It takes an extraordinary 248 years to complete one full orbit around the Sun, meaning that since its discovery in 1930, Pluto has not yet completed a single orbit. However, its orbit isn't the only distinctive feature. It's also highly elongated compared to the more circular orbits of the larger planets. Additionally, Pluto's orbit is tilted by 17 degrees relative to the plane of the solar system, making it one of the most tilted orbits observed. This extreme tilt, combined with its elongated shape, adds complexity to Pluto's journey through space. A particularly fascinating aspect of Pluto's orbit is its interaction with Neptune's orbit. For around 2 decades during each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect in terms of planetary positioning. This raises an important question. Why haven't Pluto and Neptune collided yet? The answer lies in the gravitational forces at play within the solar system. Immediately after Pluto's discovery, astronomers were puzzled by its orbit. Unlike the other planets, which follow relatively flat, aligned paths within the solar system, Pluto's orbit is tilted and elliptical, making it a subject of intense study. The fact that Pluto's orbit crosses Neptune's doesn't automatically result in a collision due to a gravitational interplay that stabilizes the two orbits. This balance, referred to as the three-body problem, illustrates how Pluto, Neptune, and the Sun interact through their gravitational forces, like predicting future positions based on their current motions and forces exerted upon each other. This phenomenon highlights how Pluto's, Neptune's, and the Sun's gravitational pull ensures the two objects never collide. Astrophysicists note that this stable interaction is maintained by a mechanism called libration, which ensures that when Pluto crosses Neptune's orbit, it does so at least 90 degrees away from Neptune, thus ensuring that the two bodies are never at the same point in their orbits at the same time. Additionally, Pluto's orbit exhibits degree libration, meaning it oscillates or shifts around its path. This mechanism further reduces the risk of collision. Another important factor in Pluto's orbital stability is the gravitational wobble effect, known as VZK wobbling, which explains how the gravitational pull from Pluto, Neptune, and the Sun influences each other, helping to maintain Pluto's orbit despite its seemingly erratic path. The three-body problem and these forces that govern the celestial motions are critical to understanding how planetary orbits evolve. These interactions not only shed light on Pluto, but also enhance our knowledge of the broader workings of the solar system. Numerical simulations conducted in the 1980s revealed that while the stabilizing forces help keep Pluto's orbit stable, slight changes in its initial conditions could cause its orbit to become more erratic over long periods. Despite such potential irregularities, Pluto's orbit has remained relatively consistent over millennia. Recent models have further highlighted how planets like Jupiter, Saturn, and Neptune help stabilize Pluto's path. For example, Neptune and Pluto follow a resonant orbit, meaning for every 2 orbits Pluto completes, Neptune completes 3. This resonance is crucial to maintaining Pluto's orbital stability. However, Neptune is not the only planet influencing Pluto's orbit. Jupiter's gravitational influence also plays a significant role. Even Saturn has been shown to help stabilize Pluto's orbit. These simulations suggest that Jupiter's gravity alone could maintain Pluto's orbit for billions of years, if not indefinitely. The cooperation of Neptune, Jupiter, and Saturn is thus essential for ensuring Pluto stays on its current course. Without these stabilizing forces, our solar system would be more chaotic, with bodies like Pluto potentially colliding with others or being ejected from their orbits entirely. Studying such interactions not only helps us understand Pluto's orbit, but also gives us valuable insights into the larger workings of the universe. Given this knowledge, Pluto's orbit becomes even more intriguing when considering theories of a potential collision with Neptune. The study of Pluto's complex orbit demonstrates the dynamic nature of our solar system and how the forces acting on one object can impact the entire system. It also reminds us that even seemingly chaotic orbits can still achieve a balanced state through these intricate interactions. The principle of orbital resonance plays a key role in this balance, explaining how Pluto's position and velocity, even with an irregular path, can still maintain stability over time. Programs simulating these orbital mechanics have provided valuable insights into how Pluto's orbit interacts with those of other celestial bodies, including Neptune. Small adjustments in the model's parameters can show how even slight changes in Pluto's position or speed could significantly alter its orbit. Despite stabilizing factors such as asymmetric libration and degree libration, Pluto's orbit can still be unpredictable. Small variations in Pluto's initial conditions could lead to large shifts in its long-term trajectory. Nevertheless, despite its apparent unpredictability, Pluto's orbit remains remarkably stable over billions of years, indicating an underlying order to its movement around the Sun, even when it seems chaotic. This unpredictability presents a challenge for astronomers, who must account for the evolving nature of planetary orbits. Although numerical simulations are invaluable for predicting celestial behavior, they also demonstrate the limitations of our models. These simulations are heavily reliant on the accuracy of their initial conditions, and even the smallest error can drastically change the results, making precise predictions difficult. Pluto's erratic orbit serves as a reminder of the constantly changing nature of the universe. While astronomers have made remarkable advances in understanding space, Pluto's unpredictable path illustrates how much more remains to be discovered. The study of gravitational effects from giant planets like Jupiter, Saturn, and Neptune on Pluto allows scientists to gain important insights into the solar system's larger dynamics. It reveals how the positions and motions of individual planets can have far-reaching consequences for the stability of other objects within the system. Despite these stabilizing influences, leading astrophysicists have expressed concerns about a possible collision between Pluto and Neptune. Neil deGrasse Tyson, a prominent astrophysicist, offers a unique perspective on the mysteries of our solar system, using Pluto as an example. Tyson, who helped reclassify Pluto from a planet to a dwarf planet, emphasizes the importance of continually evolving our understanding of celestial mechanics. Tyson argues that Pluto's reclassification was not a loss, but a necessary adjustment as our knowledge of the solar system deepens. He views Pluto's unusual orbit and its interactions with Neptune as proof of space's inherent unpredictability. Although Pluto's orbit is stable for now, Tyson cautions that it could change significantly in the future. This possibility highlights how much is still unknown about the forces shaping the solar system and their broader implications. Tyson's perspective underscores the unpredictable nature of space, reminding us of the complexities of celestial mechanics. His analysis of Pluto's orbit in relation to Neptune emphasizes that even long-studied planetary movements can hold surprises, despite apparent stability. Tyson suggests that this situation could evolve over time due to dynamic forces at play within the solar system, which remains largely unpredictable. The reclassification of Pluto as a dwarf planet was a move that sparked public controversy, but aligns with the growing body of knowledge about our solar system. Tyson explains that this adjustment was necessary to refine our classification system for celestial objects as our understanding and tools for exploring space continue to improve. While no longer considered a full-fledged planet, Pluto remains an important subject for scientific study. This evolving understanding extends beyond Pluto's classification and contributes to broader discussions about the stability of our solar system and the forces governing planetary motions. Tyson's work and that of other scientists continue to illuminate the complexities of celestial mechanics. These discussions about Pluto have wide-ranging relevance for our understanding of the universe. Michio Kaku, another key figure in the conversation about Pluto and Neptune, adds further insight into the potential risks and dynamics at play. His work builds on Tyson's, exploring how small shifts in Pluto's orbit could lead to a collision with Neptune or impact the stability of other celestial bodies. Kaku's contributions help clarify how we might predict and possibly mitigate these risks as our understanding of distant solar system objects grows. To better understand the possibility of a Pluto-Neptune collision, scientists rely on advanced simulations and models that track the gravitational forces between these two bodies over time. These models take into account the complex interactions between Pluto and Neptune's orbits, as well as the influence of other planets like Jupiter and Saturn. This research is essential not just for understanding Pluto's future, but also for refining our ability to predict the behavior of other objects in the solar system. Although Pluto and Neptune currently maintain a relatively stable relationship, uncertainty about the future of their orbits remains. The intricate gravitational dance that keeps the two planets on their present paths could change over vast periods of time. Even the smallest variation in their initial conditions could shift their orbits, potentially leading to a collision or another disruptive event. This unpredictability underscores the limitations of our current knowledge and the challenges ahead in studying the long-term dynamics of the solar system. Understanding the forces that affect Pluto's orbit is just one part of a much larger puzzle, and it provides valuable insight into the broader workings of our solar system. The interaction between Pluto and Neptune exemplifies the delicate balance needed to preserve planetary orbits not just for these two objects, but for the entire solar system. Studying Pluto's orbit is therefore vital for gaining a deeper understanding of how celestial bodies interact with each other and how the solar system maintains equilibrium. As our exploration of space continues, studying Pluto and other far-off objects becomes increasingly important. These objects, though distant, hold valuable clues that could help us understand the origins and future of our solar system. By examining Pluto's unusual orbit and its potential interactions with Neptune, scientists are learning more about the forces shaping our cosmic neighborhood. These discoveries may have broader implications for the study of other distant objects, including exoplanets and stars in remote galaxies. Ongoing research into Pluto and Neptune also serves as a reminder of the need for continuous learning in astrophysics. As Tyson and Kaku have adapted their views in light of new findings, future scientists will need to remain flexible and open to new ideas. The universe is constantly changing, and our understanding of it must evolve as well. As technology advances and our exploration deepens, more surprises about planetary orbits and the forces governing them will likely emerge. In conclusion, the potential for a Pluto-Neptune collision remains an intriguing and complex topic that continues to captivate scientists and the public alike. The unique orbital features of Pluto, coupled with the complex gravitational interactions at play, make this subject of great interest. While the stability of Pluto's orbit is reassuring for now, the possibility of future changes serves as a reminder of space's unpredictable nature. As we continue to explore Pluto, Neptune, and other solar system objects, we gain deeper insights into the mechanics of our cosmic neighborhood, which not only enhance our understanding of the past and present, but also shape our predictions for the future, helping us better comprehend the vast and dynamic universe we inhabit. The study of the relationship between Pluto and Neptune offers crucial insights into the nature of the solar system. Understanding their orbital dynamics helps astronomers refine models of how distant objects interact within the vast expanse of space. By continuously observing these interactions, scientists can not only predict potential future events, but also better understand the forces that govern the movement of planets, moons, and smaller objects across the cosmos. These advancements in space exploration are not just about answering specific questions, but also about developing broader theories that apply to a range of astronomical bodies. The research on Pluto and its orbit is an example of how focused studies on individual celestial objects can lead to significant discoveries about the universe as a whole. As our methods for observing space become more sophisticated, we may uncover even more complex behaviors in objects that we once thought were too distant or too small to be of interest. In addition to the scientific curiosity surrounding Pluto and Neptune's orbits, the ongoing debate about Pluto's classification also highlights how our understanding of space is always evolving. As we gather more data and develop better technologies, what we know today may look completely different tomorrow. The journey to understanding Pluto's role in the solar system is a perfect illustration of this constant growth in astronomical knowledge. The idea of a potential collision between Pluto and Neptune also underscores the dynamic and interconnected nature of the solar system. While this event may seem distant or unlikely, the gravitational forces at play between planets demonstrate the complexity of their movements. Even the smallest force, such as a shift in the orbit of one planet, can set off a cascade of changes that ripple through the entire solar system. This interconnectedness is a reminder that space is not a static environment but a constantly changing and evolving system that can surprise us at every turn. Moreover, the fact that a collision between Pluto and Neptune could be prevented by subtle, gravitational forces over billions of years speaks to the precision and balance inherent in the solar system. While many might think of space as chaotic and unpredictable, these phenomena show that there is an underlying order and stability governing the motion of the planets. This knowledge has not only deepened our understanding of planetary orbits but also shown how these mechanisms have likely shaped the development of our solar system and could continue to influence its future. As we venture deeper into the study of Pluto and Neptune, the ongoing discoveries will undoubtedly push the boundaries of our understanding. Scientists continue to refine their models and conduct simulations to predict the behavior of distant objects, helping to uncover the deeper workings of the universe. Each new finding, no matter how small, contributes to a greater picture of the cosmic forces that govern our solar system and beyond. In essence, the potential for Pluto and Neptune's collision, though remote, serves as a captivating reminder of the incredible complexity of our solar system. It is a testament to the ongoing quest for knowledge and a reflection of how scientific understanding constantly evolves with new observations. While our grasp of these distant planets and their interactions may never be entirely complete, each discovery brings us closer to unraveling the mysteries of space, paving the way for future generations to explore even deeper corners of the cosmos.